Sairam to all of you. Welcome back to this session of general principles and processes of isolation of elements. In the earlier sessions, we have seen about the occurrence of metals. Then we have seen how we could concentrate those ores. And finally, we have now come to a process where we are extracting metal from these crude ores. This part is now important where we use certain principles of thermodynamics which we happen to study in our first year. So if you can just recall certain aspects that were studied in first year, especially in the case of thermodynamics, and also we utilize certain principles of equilibrium. You happen to come across an equation which was given by delta G is equal to delta H minus T delta S. I am sure you are aware of the terminologies that these represent. G indicates Gibbs free energy, the free energy which is available for a process to happen. The second component that is available here is enthalpy. Enthalpy is the energy content or heat content present in the system. T represents temperature and S represents entropy of the system. The symbol delta indicates changes in these factors whenever certain reactions take place. So just to brush up all those that we have studied, we will first see what is this terminology delta S. We name it as change of entropy. So first thing we need to know is what is entropy. Entropy is defined as degree of randomness. Whenever a molecule is present at a particular place, if it is a solid, in case of solid, we happen to study that solid molecules are pretty close to each other. Being in strong attraction, they will be tightly held with each other. Come to the next stage, that is liquids. Liquid molecules rather generally flow across a surface and therefore the molecules can be found a little far away. So when you compare the molecular structures of a solid and a liquid, you will feel that the solid structures are tightly packed, liquid molecules are spread a little. But then come to gases. Gases have molecules which are spread all across in their places. Now what does this mean? The gas molecules are randomized across the place, whereas solids are particularly having a certain arrangement as such. So in this case, what you can understand is gases have very high entropy, whereas the entropy in solid is pretty less. One thing has to be understood here is that entropy is a degree of randomness. It is not a degree of stability. It is rather a degree of randomness. That is why for gases, the entropy value happens to be in positive states generally. For liquids, the value of those will be reduced, and when you come to gases, especially in this case, you might find these in negative aspects as such. This is considered if this prophecy was for stability. But given that we discuss entropy as the degree of randomness, gases being having highest randomness in them will rather have entropy as positive value, whereas solids will generally tend to have negative values. The value for liquid will be quite in between them. So having understood this entropy factor, we will see how it is important for our metallurgical processes. So taking back this equation now, delta G is equal to delta H minus T delta S. Delta H generally for a reaction, whenever these metallic reactions takes place, they may be exothermic in nature. So in this case, when we do certain case studies where case 1, I am going to consider here that my delta S value is positive in nature. In this case, the equation remains as it is and delta G will be equal to delta H minus T positive value of entropy By mathematical formulations, we are aware that a negative into positive factor will always be negative. Now, what does this condition mean? Irrespective of the delta H value, if temperature increases, this value of delta G will slowly increase in their negative factor, because this entire factor T into positive entropy is in negative form. So therefore, an increase in temperature, so when we consider a case of increase in temperature, we realize that as the temperature increases, delta G becomes more and more negative. Also remember the application of delta G. If delta G is negative, this condition indicates that it is spontaneous process. If delta G is positive, it indicates a non-spontaneous process. Now this case is applicable when we believe that the entropy of the system is positive. When the temperature increases, delta G goes more towards the positive value. Now in this case, if we see, take up another case, that is case 2. Supposing delta G is equal to delta H minus T, and let me consider my entropy to be negative. Now again, by mathematical formulations, we are aware that minus into minus happens to be plus. So this entire form will now turn out to be delta G is equal to delta H plus this entropy value in this special case. If there is an increase in temperature now, what will happen is the positive factor will go on increasing. Therefore, delta G will tend to become more and more positive. So here what important basic points we need to know is that if the entropy is positive, an increase in temperature will lead it to the spontaneous reaction, because you are getting delta G equivalent of negatives. In case where entropy is negative, we get that the entire factor happens to be positive, and therefore in this case, as temperature increases, the delta G value will become more towards positive value. And therefore, as temperature increases in these cases, these type of reactions tend to be non-spontaneous in nature. So this is one basic point where we had studied as a theoretical aspect in thermodynamics, but the application of that is seen here. So how it is applied, we will see further in the Ellingham diagrams, but before that, we need to know one more important aspect. If you remember, in the thermodynamics, we came across something like Hess law, which said that if there are multiple steps in a reaction, the overall reaction energy will be equivalent to the energy involved in all the steps. Suppose it's a 4-step reaction. If some are exothermic, some are endothermic, the final value is dependent on the sum of the energy involved. So therefore, it also applies similarly in this case. Supposing some reactions give delta G positive value, some give negative value, the overall value is what is considered. So for this, let us see an example. An example where iron oxide is reduced to iron. There are many forms of iron that we come across. So let me consider one temperature, that is at 500 Kelvin. It was practically observed at 500 Kelvin, it was observed that these were the following reactions which were utilized for reduction of ferrous oxide to iron. So what do we mean by reduction here? Basically, the oxygen atom should be removed from the iron oxide which is present. So in this cases now, let us take the first example where iron oxide is undergoing certain type of reduction, and when you undertake a reduction, you definitely need some reducing agent. So that reducing agent, let me consider it to be carbon in this case. What is the role of a reducing agent? It helps in reduction of the above ore. So what are the different reducing agents possible here? One is carbon, the other one is carbon monoxide. In these cases, depending on the practical analysis, we consider any one of these systems. So for this example, I am going to consider the presence of carbon in this case, where I am going to react it with oxygen molecule. This reaction, if it has to become carbon to carbon monoxide, if it is an incomplete combustion, this is the balanced chemical equation that you get. And similarly, iron, if it is to be reduced, you get it as Fe plus O2. Once again, balancing of this reaction, you can get it as 2FeO giving rise to 2Fe plus O2. So what are certain practical values that you come across for this? Practically, it is seen that the delta G values in both these cases, in practical analysis, you happen to come across as plus 400 kilojoule per mole, and this value is around minus 320 kilojoule per mole. Now, what is the overall reaction that is taking place? So, how do we identify the overall reaction? We know very well that the oxygen on the left hand side gets cancelled out with the oxygen on right hand side. This reaction will be 2FeO plus 2C giving rise to 2Fe plus CO. It so happens that the 2 is a common factor in all of this. So rather what you can take here is that FeO plus C giving rise to Fe plus CO. And when we calculate the delta G of this compound, we get it as plus 80 kilojoule per mole. Now you know very well that if delta G value is positive, this is a non-spontaneous reaction, which will mean that this carbon cannot act as a reducing agent in this condition. Now remember that in all these phenomena, what is the question of entropy in these cases? This form is solid in nature, this is solid in nature, this is gaseous in nature. Similarly here, this is solid, this is gas, and this is gas. What we realize here is that there is only a solid form in the reactant side, whereas the product side has gas. And remember that gases have high randomness because of movement of molecules. So the entropy value in this case will be generally higher than the components, whereas here also if you see, there is only one molecule of gas, whereas there are two molecules of gas being present here. So these increase in these entropy systems that you consider will lead to the values that are present in these cases. So this is one example. The moment I change this temperature to say around 1000 Kelvin, the reaction happens same. There is no difference in the reaction that is taking place. But practically, we observe that change in delta G values. So what are the practical values that we have? This happens to be at 300 kilojoule per mole, whereas this one at 500 kilojoule per mole. And when you totally calculate it, you will get it as minus 200 kilojoule per mole. At this temperature, at a higher temperature, since the entropy is increased, because when temperature increases, molecules get more energy to move around in the system. So with an increase in entropy, we see that the delta G value has come towards the negative values, and these negative values now indicate that this reaction is spontaneous in nature. So what do we understand is that at various temperatures, certain elements can act as a reducing agent. At a lower temperature, this could not act as a reducing agent because you found out that the delta G value was positive. Whereas at a higher temperature, the final delta G value that you are getting is minus 200 or so. So this value in a negative form indicates that this reaction can be spontaneous in nature, and this agent which is there, the carbon which we take here, is in the form of coke. This agent can be acted as a very good reducing agent. So this is how the relationship between temperature, entropy and spontaneity of a particular reaction is determined, thereby making us realize how do we choose our reducing agents in these cases. Thank you. Sai Ram.